time of record starting.
Okay, thank you. So welcome to the Bioengineering Department Seminar. Today we are very excited to welcome a very accomplished and inspiring speaker, Professor Sauro Succi. Sauro serves as Senior Research Executive and Principal Investigator at the Center for Life Nanosciences at La Sapienza of the Italian Institute of Technology, and he's a research affiliate of the Physics Department of Harvard University. His research spans a broad range of topics related to complex states of flowing matter. Today, he'll be speaking to us about his recent work with simulations of Biosoft systems. So Sauro has a very long list of awards and achievements to his name, including being one of the founders of the Lattice Boltzmann method, used extensively in fluid dynamics and soft matter physics. So I'd like to borrow the idea from Naomi, who usually asks the speakers to share something not on their CV. So I asked Sauro, who pre-COVID would be found traveling all over several times a month, how he had managed his newly found free time. And as it turns out, he used it quite productively. He has finished up his new book, Sailing Ocean Complexity, Lessons from the Physics Biology Frontier. So that's with Oxford University Press, and hopefully it will come out in sometime in 2021. So without further ado, thank you so much for being here today, Sauro. So please take it away.
Thank you, Brenna. Can you hear me well, by the way?
Yes.
Good. So thank you for this very nice introduction. Thank you for the invitation. I'm very happy to be here today. But as a matter of fact, as we were discussing off the record, I would be much happier to be there instead of here. But that's how it goes this day. So let's hope that we will have an opportunity to meet again in person in the future. Right. So today, my talk I chose as a title, Biosoft Simulation Across Scales, and I have a lot of topics. I'm not sure I will have time to go through all of them, but it doesn't really matter. The idea is to share a few thoughts regarding the activity that we are currently developing within my ERC, which is now in its fourth year. And ERC has to do basically with states of matter which are based on droplets instead of molecules. Somehow it's a kind of jesty way of putting this kind of research in perspective. But I think during the talk I will mostly be illustrating simulation of what I call Dropland. And if as time allows, I will try to cover a little bit over a topic on specific topic on how to simulate deep sponges, which was a lot of fun. Just for the sake of fun, I will hope I will have time to discuss that. And maybe as a second part of the talk, I will go from Dropland to a little bit more down into the molecular world, and described how we use mesoscopic method like Lattice Boltzmann, as Brenna was mentioning before, to address problem more in the molecular scale, like the ion transport in neuroreceptors, depending on time. Okay, so let's get started. The project is called COPMAT, the ERC grant, which stands for Computational Design of Porous Mesoscale Material. And again, to put it in a colloquial way, let's say that we're asking a very simple and naive question. What if molecules would be replaced by droplets? What would the world look like? That's what I call Dropland. And more seriously, what kind of droplet-based materials can we envisage and design, simulate and design, and how do we realize them in the lab? I should say that it's a very interesting subject because it's highly interdisciplinary. Of course, the framework is soft matter. So we are talking basically KT physics, the physics, I mean, the energy which are typical of biological world. And it turns out that, at least this is my perception, that you can have fun on different fronts. I don't know whether you can see my pointer. Can you see that? Oops. So from the point of view of basic physics, certainly it's interesting because you have to study basically the property of non-equilibrium pattern formation, so the configuration of this droplet under flow. And this underflow is very important. So we are, by definition, these are driven systems far from equilibrium. And as you know very well, far from equilibrium, there are enormous opportunities, states of matter that would not exist at equilibrium. It's a big challenge from the numerical point of view because, as you may well imagine, this physics covers several decades in space and many more in time. And so the numerical methods are challenged and challenging. And that was basically the hardcore of my project, where the motivation of the ARC. From the point of view of material science, the idea is that out of these new states of matter, it should be possible to envisage or conceive new materials. And frankly speaking, I really hope that there will be a scope for discussing potential collaboration, because it seems to me that the bioengineering department is just perfect for this kind of discussion. I'm only presenting, if you wish, my part of the story, which is the simulation, but the things become really exciting when you can match with people who eventually design materials and experiments, real materials and real experiments. So I hope that this seminar might help setting up some collaboration, concrete collaboration. Of course, there is the engineering part, which is very related to the material, and the engineering and applied physics part has to do mostly with microfluidic experiments, which have really known a tremendous progress over the last 20 years. It is just because of the major advances in microfluidics that you can generate these mesoscale materials. And finally, and that's again related to all of the above, at the end of the line, it would be fantastic if, based on these materials, one could conceive new biomedical devices. Biomedical is the main application, I would say, but there are for sure applications of these materials also in energy and environment. So as you probably know, but I don't know now what my audience looks like. I assume that there are undergrad and young students. So the fascinating point, at least from my perspective, is that these sub-mesoscale materials are weird and interesting because in the end, as you will see, we are talking the three basic states of matter, gas, liquid, and solid, on top of this slide, which are just mixed together in different proportions. But the point is that even though, take for instance a foam or an emulsion, mayonnaise is an example, ketchup, they are made actually by, mayonnaise is liquid, oil and water, as you know very well, and even though both the two oil and water separately have a very simple rheology, they are so-called Newtonian fluids, namely they deform proportionally to the stress that you exert upon them. When you combine them together in proper ways, the result, namely mayonnaise, does not behave Newtonian at all. And the reason is that there are genuine and new properties of these materials which are not shared by any of the three basic states, gas, liquid, and solid. And this is due to the fact that there is configurational degrees of freedom which organize very nonlinearly, and there are, especially in the dense regime, very fascinating and difficult problem related to many-body interactions. So it's really a beautiful framework and very rich. At least on my side, I'm really enjoying that. Now, one of these materials, and it has a fascinating name, is called soft flowing crystals, and they exist. I mean, this is an experiment performed some 15 years ago in Harvard. And just to tell you what I mean by a materials made of droplets instead of molecules, this is a microfluidic experiment. You have a stream of oil coming from the left, the orange arrow, and there are two streams up and down of water, the blue arrows up and down. So the point is that oil enters the microchannel, but it is squeezed by the two jets of water up and down, and as a result of the squeezing, the jet breaks out. And depending on the flow rate of oil to water, if the flow rate is below a certain value, what you generate are disordered configuration of small droplets, which looks like a gas. It's a bubbly flow, okay? So that would be the analog of the gas state of the mesoscale material. And as you increase actually the flow rate of the oil, which is called dispersed phase, because you have water, which is a continuous phase, and you have the droplets dispersed within the water. As you increase the mass flow of the oil, of course, you have a dense regime, which is the second. I'm not sure. I don't see. Here it is. Can you see my pointer, Brenna?
Yes, we see it.
Okay, good. So if you take this, I don't see myself. So every now and then it disappears, and I don't know where I am. Never mind. So the second panel from the bottom, from the top, is you have more oil, so the droplets get closer to each other, and that is something that here is written as foam because I think because there is a gas, but it could be the same for the case of oil and water. That would be an emulsion, which is somehow the analog, if you wish, of a liquid. And then as you keep increasing the mass flow of the dispersed phase, you generate sort of solid state materials. As you can see, that the panel in the middle is called, it's an honeycomb connectivity, looks like a solid. And as you keep increasing, you just change topology. So the connectivity of the so-called X3, the middle is 6, and now you switch, there is a sort of plastic rearrangement, and you generate a different crystal with a different connectivity, the connectivity is 3. And finally, you switch again to another kind of solid, which is a sort of one-dimensional crystal, X1 is called. 3 to 1 is basically the connectivity. And the amazing thing from the experimental point of view is that this transition, if you want, between the different, say, gas, quote unquote, liquid and the different solids is very simply controlled by the ratio of the mass flow of oil versus water. And they tell me, apparently, I mean, this configuration, as you can see, are very regular and they are highly tunable. So it looks like this is a very efficient way of generating crystals of droplets, which have many uses. A typical use is for bioengineering, namely, there is some surfactant inside the water. So at the outlet of this experiment, you would shine ultraviolet light. The polymer inside the water would crystallize, so water becomes a sort of plastic media. The oil can be evaporated away, and the result is a scaffold with oils which are very regularly spaced. And so you can produce this on an industrial scale. And this is a story I heard. I never did the experiment myself, which can have a lot of application, typically in scaffolding for tissue engineering. And again, it's a highly controllable and simple setup, and that's why people got interested in this. I think a big name, George Whitesides, I'm sure you know him, I think is still very active in Harvard. This is an example of what I meant by the fact that Newton plus Newton is not Newton again in this business, because the rheology, the way these materials flow and respond to solicitation, is by no means linear one, even though the oil and water separately are Newtonian. So here is an example. This is the flow rate of the I think this was the gas in the experiment. Let's say that this is oil, okay, versus the pressure which you have at the inlet of the experiment. And as you can see, the ratio of the two is not a linear relation, so the behavior is non-Newtonian. And you can see also the topology of the different crystals. And all of a sudden, if you keep actually increasing the pressure, what happens? There is a crisis, this rectangle, dark rectangle, and you switch, you have an unstable state, and you switch to a different branch, which has a different exponent. And the reason why you have this kinetic structural transition is because the fluid is just rearranging from one topology to another. And you may well understand that the way this material flows depends on the friction between the droplets inside, how much area is exposed to the confining walls, and that's why the rheology is really very nonlinear and very complicated. So the question is, how do we model this complex phenomena using computational schemes? And as I will make clear, I don't want to spend much time on this, but the point is that continuum methods, say Navier-Stokes equations for non-ideal mixtures, are unwieldy because these are flows with a very high surface to volume ratio. So if you have methods which track the interface between oil and water, they have an enormous amount of work to do to track this interface. On the other hand, if you use atomistic method, the scales here are of the order of centimeters, and I mean, atomistic methods are still too short. I mean, there is no way you can reach up to the scale of the experimental interest with molecular dynamics. So it looks like this is a perfect playground from the mesoscale technique. And as I'm going to show in a moment, we are talking basically 6 decades in space and possibly twice as many in time. And what we are using is Lattice Boltzmann. It really looks like a perfect playground for Lattice Boltzmann, even though I have to tell you up front that we had to extend Lattice Boltzmann quite significantly. The project started 3 years ago, and 3 years ago there was no Lattice Boltzmann available on the market, so to say, which would actually be able to handle the complexity of this regime, because these are very dense regimes. So one word of Lattice Boltzmann. If you have questions, you can ask Brenna. She's an expert in that. But just to convey the idea, in Lattice Boltzmann, what you do, you basically replace the continuum word. Continuum means this is a real gas. The molecules can flow up and down, left and right as they best pleases them. In Lattice Boltzmann, you basically condense the molecules, you crystallize the molecules on a crystal like this, and they have very limited freedom. They can only move along the direction pointed by these arrows, and as you count them, they are 18, 6 to the nearest neighbors on the faces, another 12 to the edge centers. And there is also a standing particle called spectator. And if you sum them up, they are 19. So you basically replace an infinity of possible velocity with just 18. And just to make a very long story short, and if you choose this symmetry of the crystal properly means that you secure the proper symmetries and conservation laws, believe it or not, this is good enough to simulate exactly the behavior of a continuum fluid, okay? And again, it's a long story. Formally is you basically, V is the velocity, and you just sample, if you wish, the velocity of your gas, of your liquid, according to a discrete set, which is indicated by C sub I runs from 0, the spectator, B is historical, stands for bits, because in the early days, these were Boolean particles. And in this case, you have 19, and this is not a cartoon. This is what you would use, as we speak, to do 3-dimensional simulation using Lattice Boltzmann. There are several good points about it, but this is not a lecture on Lattice Boltzmann. The only point I want to make is that if you compute the fluid quantity, F is the Boltzmann distribution function, namely the probability of finding a molecule at position X that would be the center of this crystal lattice cell, with velocity v at time t. And if you want to generate hydrodynamics, say if you want to generate the fluid density, what you have to do is to integrate over all possible velocity. And in the continuum, this would be an integral like this, okay? F x b d, and A of v is any property, microscopic property. It could be momentum, could be energy. And you replace, actually, in the Lattice Boltzmann, this integral with a discrete sum. And for those of you who have seen the Gaussian quadrature, you know that if you select the collocation points, the discrete speeds properly, these integrals are exact. Exact means exact. If you use, say, a certain number of collocation point discrete velocities, the low order moments up to a certain degree of the polynomial in V, the sums are exactly like matching the integrals. That means that in principle, you can see why actually you can reproduce hydrodynamics not more or less, just exactly. And another property, which is fundamental, I just tell you in word, and there is a lot of course, if you are interested, you can always, I will be happy to discuss in full detail. The key property is that in this formalism, the information always travels along straight lines. This is an enormous advantage because by traveling along a straight line, suppose you are a particle moving right, the arrow, blue arrow pointing right, at time t, this particle will just travel to the center of the phase. And just travel means that the value which I had at the center of the cell at time t is just transferred as is to the center of the cell, and this is an exact operation. In computer terms, you are just shifting a memory location. This has zero round off. This is perfect. And this property, believe it or not, looks very simple. It's just key. So I would say it's the most important property of the lattice Boltzmann. And please contrast this with the fluid dynamic representation of advection, in which you have the velocity times the gradient of the velocity, u grad u, right? Which means that the information moves along the material lines defined by the fluid velocity, which is a complicated function of space and time. So in a way, the fact of using kinetic theory, discrete kinetic theory, allows you to move information along straight lines which are always the same no matter how complicated the hydrodynamic signal. This is the key of lattice Boltzmann. And I will stop it here because, again, I want to focus on the application. If you have questions, of course, I will be mostly pleased to go into detail. Now, application. Many, of course, I will not cover all of them, but it's rather amazing the number actually of materials that we have been able to somehow explore using this technique. But let me just give you the physical ground. I've told you before that we are talking microfluidic experiments, so that's the typical case of the soft flowing crystals. Now, I really would like to speed it up a little bit. The point I want to make is that there are many forces in play. The flow is driven. This material only exists under drive, and the drive is, of course, the pressure you have to put across the microchannel, okay? Then, of course, you have viscous, you have the inertial forces, okay, just the one which would drive, you know, nonlinear turbulence, but we don't have turbulence here. You have viscous forces, and viscous forces are responsible for jet breakup. When I told you that the oil jet is squeezed by water and generate droplets, is because you have, this is a very confined system. These systems are millimeters in the in the vertical direction. They are actually less than millimeters. So they are very confined system. And the main player are the capillary forces, surface tension. And capillary forces, as you know, tend to kill droplets. So they work against Dropland because capillary forces want to generate just a single droplet to minimize surface to volume. And that's why in the experiment you put surfactants that we model as NC stands for near contact. Near contact means that when two droplets are just getting, say, 10 nanometers apart, and the droplets are of the order of 100 microns in diameter, then there are forces which keep them apart and prevent coalescence. And I have to tell you that this is precisely the main ingredient that was missing in the lattice Boltzmann models up to 3 years ago. And that's the major, I would say, achievement of our ERC so far, is just a clever way of accounting for these forces, which are key. If you don't have these near contact forces, you would coalesce, the crystal would melt down, and bye-bye Dropland, right? Now, I have a lot of information here, but I want to keep it simple. Again, I will be mostly pleased to take questions later or maybe in the coming days. So for the simulator, there are two regimes. The easy, this is a walk in the park, as we say. If the droplets, if you are at low volume fraction, D stands for disperse oil, C for continuous. The droplets are far apart. Delta is typically the mesh size I can afford on my computer. And as long as h, which is the separation, if you wish, between the film, if you wish, between two droplets, if h is comparable or even higher than the droplet diameter, which again is of the order of 10 to 100 microns, life is simple, and as you say, beer is cool and life is good, because you can resolve all the relevant scale for the rheology, and that's not challenging, and you don't need to account for near contact interactions. The challenging scenario, which is the one relevant to Dropland, is the scenario where the droplets actually get in touch, close touch, and when h, the film length, is, say, 10 nanometers. And if you want to resolve 10 nanometers, say you have a mesh spacing of 1 nanometer, but your device is 1 centimeter. And here something is wrong. You have 6 or 7 decades and no method, there is no method on this planet which can take 7 decades in a single swoop. You have to do something. And Lattice Boltzmann is like any other method. Somehow, what you have to do is, I mean, you can take many roads, but what we did was trying, in fact, to implement a sort of subgrid model for these near contact forces. Subgrid models mean that we cannot afford 1 nanometer in the simulation because we definitely want to simulate centimeter. We want to be relevant to the experimentalist and to the people who design the materials. And what we can afford is perhaps 1 micrometer as delta, which means that we have to coarse grain the near contact interaction heavily. 2, 3 orders of magnitude. And as you know, coarse graining is an art. You have no guarantee that it will work. It really depends on how the scales are coupled one to another. And I can anticipate the bottom line. The only reason why our project worked and worked very well is because these near contact interactions somehow can be coarse grained effectively. Somehow they do not propagate all the way up to the scale of the device, and you can somehow model them in a relatively simple way and without actually affecting the global rheology of your system. So again, to give you, so h is a typical scale of the device, say 1 millimeter, 1 centimeter. The droplets are anything between 10 and 100 microns, and the delta we can afford is of the order of 1 micron, and so that means that we have to coarse grain basically from 10 nanometers to 100 to 1 micron, so a factor 100. Brenna, what do you say? I don't think I should bother people with technicalities on Lattice Boltzmann, or should I? You don't know. I'm embarrassing you. Well, let me tell you one thing, just very, very quickly. I mean, it could be a full seminar. Let me tell you the funniest part of the story. In Lattice Boltzmann is good, is excellent, but is not perfect. And one problem we have in Lattice Boltzmann is that when you do simulation in 2D, that would be the grid. And if you have fast-moving droplets, the droplets inside is here and outside is, they're both blue. This would be, for instance, oil and water, which have the same density. But if the droplet moves fast, and if you have, say, water moving in air, like in a diesel engine, so a big density contrast, this grid would not be enough, and you would need more discrete speed. And the result is that the simulation just sends you a strong message and generates artificial micro recirculation. You see these vortices, and as you can see, they are just a photocopy of the lattice underneath. That tells you that your scheme is not good enough. And now, assume that you have 2 droplets, and these things do not exist. They are so-called computer hallucinations, right? And if you have 2 droplets coming very close to each other, they would just interact through computer hallucinations, and that would be a disaster, right? So these are called spurious currents in the Lattice Boltzmann jargon, and they are a major concern for flows with high density gradients and high velocity. Happily enough, our soft crystals are very somehow sweet in the sense that the droplets don't move fast, and oil and water have basically the same density. So again, this is a big chance that these materials actually can be studied without really running into the major troubles of the Lattice Boltzmann method, which again you would have if you have to simulate a diesel engine with spray moving very fast at high density ratio. That would be a serious problem. So we don't have these problems here. And in the end, as I was saying before, we actually implemented, there is an algorithm which I will not describe, which is called color gradient, blah, blah, blah. But the essence of the algorithm is that when you have two droplets coming nearby, you just move out. It's a sort of topological scheme. You move out of the diagonal up to a certain distance, and which is basically 4 or 5 lattice sides. And if within these 4 or 5 lattice sides you meet with another interface, then you apply a given force, which typically goes like the inverse power 4 of the distance. And this somehow mimics the presence of a surfactant. And it's very simple, actually. It's a complication with respect to the standard lattice Boltzmann, but still is something that you can manage quite efficiently. And once you, in fact, inject this near contact interaction, then you can do things that you would not be able to do otherwise. And this slide is probably not very impressive for you. It is for me, because it took to us 3-4 months before we could actually, I don't have the experimental movies, but the experimental situation is pictured above. You can see that there is a significant similarity. And the trick here is just, generate the droplets, and the droplets is just stumbling against the next droplet. And the trick was to prevent coalescence. Unless you put this near contact interaction and you put it properly, you would not be able to see this type of configuration. This was really the breakthrough of the project. Then there have been many refinements, but this was the major technical achievement. It's called multi-range color gradient with near contact interaction, and I should give full credit to Andrea Montessori, which is a postdoc in my group. He is just extremely good. And this is a Journal of Fluid Mechanics 2019, which really where we give the details of this Lattice Boltzmann scheme. Okay, let's now run to what time do we have? Yeah, I think I should speed it up. The application, I will just give you a bird's eye view. Each of them will be a talk on its own. So what do we do? Besides soft crystals, we study emulsions. And, for instance, one way of this could be, if you wish, density function gradient material. It turns out that this is a linear array of droplets, single dimensional crystal. And as it opens up, channels opens up, clearly there is a slowing down, and there is a sort of bogging of droplets into each other. And depending actually on the strength of these near interaction forces, and depending on the geometry, depending on many macroscopic parameters, you can generate somehow disordered crystals. And it turns out that the degree of disorder, and here we have some orientational parameters, I will not discuss them in any detail, but the idea is that by playing with the actually geometrical parameter of the microchannel, you can somehow fine-tune the topology of this disordered crystal. And in principle, I'm saying in principle because, these kind of things you can only generate the idea, but then you have to test the idea against real experiments. And we don't have much experiments on our own. We just started a collaboration with a group in Poland. And again, I'm really very serious here. If you have any interest or idea in that direction, please let's talk, because I think our tool is really pretty robust and efficient. Another project, which is, I will come to that later, which is related, and we just started that, and this is in collaboration with an experimental group, is soft granular media. If you wish, I tend to think of this as droplets within droplets, so could be cell aggregates. Suppose that these inside the white contours are cells, and the idea is that, I don't know whether you can see that, but I could probably do like this. Let me Maybe now you can see better. The idea is what happens if you take these cell aggregates and again you pass them through sort of confined geometries, which might be, in fact it is a microfluidic experiment, but in a physiological environment could be cells or cell aggregates moving in the capillaries. So I think, again, it's just an idea which I throw on the table. The microfluidic part, now we are testing one with microfluidic experiments, but we are thinking of potential application in actually this is really biophysics, biomedicine. Suppose that you have red blood cells or any kind of cells moving in the human body, and you can of course be a bit more realistic, but the essence is that you could have bifurcations. Brenner, you were doing red blood cells. Suppose we put a bifurcation. I have to tell you something. You have been struggling yourself, I know very well, with immersed boundaries. And if this method works, and I don't know, but if it works, this is orders of magnitude faster. So one standing question, which I would like to talk to you actually in detail, if you still do these things, whether we can be, I don't think we can be 100% realistic. If I take a red blood cell instead of a droplet, I would probably not be able to reproduce all the benchmark on how the red blood cell deforms as it moves through a channel. But I'm kind of confident that if I move a collection of cells, the overall rheology might be quite similar, and that you could get, say, with 10% error, but with 2 orders of magnitude faster. So again, that's an application that I would very much like to explore, but in connection with people who do the real thing. Otherwise, we cannot do better than, throwing the idea on the table, but then you have to somehow test against. Look, this, Brenner, I think, these are not red blood cells, but, maybe we can fine-tune the code so that they can be made close to what the red blood cell would do. So I think this is something, I call it cellular traffic. Put a quotation mark because I'm not sure this is realistic, but there are experiments here, okay, and it would be really very nice to see whether our method, which is really fast, it's a little bit slower than the standard Lattice Boltzmann, but not much. If gives insights, semi-quantitative insight, that would be already a great result, and that's again the same spirit. Another project, this is fun, again in the idea of biomedical microfluidics. This is something which we have just recently published on Nature Communication, and first time in my life I can publish in Nature journal without being rejected up front because I don't have experiments. So that was a big deal for us. And the idea is that you put droplets or maybe cells within a bag, micro bag, and you ask yourself, at least this is what the experimentalists told me. This was with the Weissman group in Harvard. They would like to know how the cells interact with each other, or maybe a cell with a drug molecule, and they want to keep them inside the bag, and the bag goes into a microfluidic device. And we realized, and I think that's the first time that people realize that there is, due to the flow, there is a very complicated pattern. There is vorticity pattern inside the bag, the vesicle, okay? And because of this vorticity pattern, the droplets generate very fancy kind of motion depending on the regime. We call that the dance of droplet within droplets. And the dance is guided by the vortices inside, which in turn are triggered by the gradient because this is a channel flow, microchannel flow. So again, as I was saying in the beginning, you can take fun in exploring this as a nonlinear dynamical system. There are plenty of exotic, non-equilibrium driven steady states, but there might be application, I don't know, maybe for drug delivery or again, to start to see how cells interact with a given drug, because by keeping them confined together, they get in touch closely, and so they can interact on a longer time scale than they would without being confined. So, and finally, I think this gives you an idea of what we have in mind in terms of using these computational methods for biosoft or biomedical application. And I hope that I'm not just daydreaming. I hope this can be turned into something concrete. And now I take somehow a different tangent because I cannot resist the beauty of this creature. This is a living organism. It's called Euplectella, and Euplectella is or Venus basket flower. It's a sponge. It's a living sponge. It's silicon, living silicon. And this sponge lives minus 500 meters down deep in the sea. And it's a glass that doesn't break. And apparently it has very amazing structural properties. And that it has been studied very intensely by structural biologists. And everybody thought, at least we discussed with them, and they said, well, fluid dynamics is basically irrelevant, doesn't really play any role. So we challenged the idea, and we set up a really huge simulation. This lasted basically 2 years, this project. This is a really an extreme calculation. We have 50 billion grid points because we want to resolve the texture of the Euplectella, and again, keep the total size of the device, which is about 1 centimeter. So this is really big deal in terms of high performance computing. And much to our amazement, we discovered that not only the Euplectella reduces the drag, which is expected, it's a porous medium, but I think you can see these recirculation patterns inside. They serve, allegedly, they serve 2 additional functions which were not anticipated. They feed the Euplectella with, material, little, plankton or whatever, which is trapped inside the Euplectella. So the Euplectella feeds itself through the micro-recirculating vortices. And apparently this was discovered by a friend of ours who are in the marine biology. Probably they also serve sexual reproduction because they favor gamete encounters. Don't ask me any question here because I really don't know. But the people who are more knowledgeable, way more knowledgeable than me, tell me that there might be these extra functions which were not anticipated at all. And don't quote me, keep finger crossed. The paper is with Nature. The reports are very demanding, but very, very encouraging. And any day, actually, Giacomo, who is the main author, is basically losing his sleep because any day we are expecting the final approval of the paper. And if this happened, again, I would be myself delighted because it never occurred to me to be able to go to nature, plain nature, without experiments. And this belongs in a way to porous media, as I was anticipating before, because in principle, these are called trabecular porous media. Trabecular porous media are media which are actually used to generate tissue for tissue repair, regenerative medicine. But again, I'm just throwing the idea. I cannot really be serious on how to actually generate a real-life project of regenerative medicine. Okay, Brenna, can you give me the time? I think I'm running out of time, right? Okay, we are using machine learning to detect cells instead of cars. Fine, that's another talk. And I think with the macro meso nano connection, if I'm not mistaken, I'm just 2 minutes. So just give me the flavor. Of course, like anyone, we are trying to do something in the direction of COVID. We got an extension of 6 months extension, and we are trying to see how, in fact, the S1 spike binds to ACE2 receptor, and we are doing that dynamically. Most studies so far are based on basically static scenarios. Based, in fact, on the chemical affinity, and we are trying to see whether the dynamics, and we are using, of course, here Lattice Boltzmann only does the solvent part. All the rest is done in molecular dynamics because, I mean, clearly here you need the molecular details. And along the same line, we use Lattice Boltzmann for 3-level simulation of neuroreceptors. And I just give you the idea. Of course, there is a lot of molecular dynamics, homology. I'm not the expert of that. But what I can tell you is that once we have the protein configuration, the protein is breathing, okay? And so it's opening and closing sub-Armstrong channels within this protein. And on these dynamic geometries, which are generated by the molecular dynamics, we actually run a Lattice Boltzmann solver for the ions. So what we did was to compute the ionic transport across the breathing protein, which is the neuroreceptor. And so again, Lattice Boltzmann is just part of a large-scale, multi-scale, and multi-level simulation. And in the end, if you compare basically the voltage, the voltage that the current that you drive through this, I call it molecular porous media because that's what it is, and difficult to say because there are huge error bars, but at least let's say that you can construct current voltage characteristics which can be compared with the experiments. So that's just to show the use of Lattice Boltzmann as just part of a more complex multi-scale process. So finally, and I think I'm basically on time, the bottom line of this talk is that I think the ERC was really useful. I will really point out this is my final report. It would have not been possible for us to develop this tool without the focus and the resources I could put together on this type of problems. And there will be, I think, there must be a follow-on because I think the practical part of the project should start in the coming year. And what I mean by practical part, I'm really out for, maybe it won't be myself, maybe it will be my younger collaborators. They should go out for joint grants with other institutions. And I will just sit in the background, but we are really out for collaboration with experimental groups, of course, also with theoretical groups, of course, because I think we really have something to offer to explore really a variety of materials and a variety of situations, which hopefully can be taken to the very end, namely a new device or a new material. And I really wish we can set up this discussion with you. This is part of the group. I know what you're thinking. I'm not politically correct. I just have a lady, but it's not my fault. I mean, I would very much like to have more lady scientists, but it so happened that this subject is probably not, I don't know. I mean, I just apologize for that in just emotes. And this is only part of the group. This is the hardcore group, but we have, of course, a lot of cross-collaboration also abroad. And with that, I thank you so much. I thank Brenna and Dr. Professor Kozlov for this nice invitation. Too bad, I would have enjoyed immensely to be with you in person. I think I was at Imperial College maybe some 25 years ago, and ever since I don't think I've been visiting anymore. Sorry about that, too bad, but who knows? Maybe we set up something together and in a year from now, maybe we have a chance to shake hands in person. So thank you again for your attention.
Thank you, Sauro. Thank you very much. That was awesome. Thank you. You see the hands clapping for you.
Now we have a question, correct?
Yeah, so now questions. So everyone, you can input your questions to the chat box, or if you'd like to raise your hand, you can ask a question yourself directly. So I had a question myself, Sauro, that I think you anticipated. So I was looking at at the figures you were showing, and so I see that you have the surrounding medium and droplets.
Which one, Bernard?
The multicore emulsions.
Oh, okay, the multicore emulsion. Here they come. Yeah.
So it makes it. So you have a surrounding medium, and that's treated with a Eulerian formulation, but actually the droplets are as well Eulerian themselves. So you have one that doesn't.
Yes, Bernard, that's precisely the point.
Okay.
That everything is Eulerian here. I mean, of course, we have multi-components. I mean, this is a different algorithm. It's a free energy Lattice Boltzmann, and actually, I shouldn't say that because one should do better, but each droplet, it's a different component, if you wish. But somehow which is not, I mean, you can only study few droplets. You cannot do an emulsion with that, right? Because you cannot have a different component for if you have hundreds of droplets. But for these studies, that's good enough. And so it's fully Eulerian. Each droplet is a separate, if you wish, array in the simulation. And of course, outside you have a fluid. This is a microchannel. I'm just taking a snapshot inside the microchannel. But clearly, there must be a structure in the microflow because otherwise there would not be vorticity inside and the whole dynamics would just deflate away. Everything is Eulerian, yes, definitely.
Yeah.
And there's a hands up from Christopher, I think.
I see NN in my screen.
Chris, would you like to ask your question? Oops. Sorry. Chris, are you there? Oh, I can't unmute. Haha. If you want to put your question into the chat box. Meanwhile, I wanted to.
Well, I'm kind of awkward. I don't know how to access my chat board. Can you perhaps read it for me and then you ask the question yourself instead of Chris?
Yes, and well, so he put his hands up, so he didn't put in his question into the chat, so we can't read it actually.
Okay. And this mic is muted.
Yes.
Then you should write me an email.
Yes, if you can type in, Brenna would read it for you, I think. Meanwhile, I want to make sure. So I had an internet problem in the middle of your talk. I hope it didn't freeze your presentation. I didn't see any sort of, it was like I was frantically trying to fix it for 5 minutes. Did anybody have any problem? Because if that was the case, I would like to very apologetically ask you to repeat that part, but it doesn't seem to be, it didn't cause anybody else to freeze your talk, so that's great. Okay. So Chris did input his question. Brenna, would you mind sort of taking? I'll shut up. Yes.
Yes, so this is from, this is Chris's question. So regarding the droplets with the small scale repulsion term, does that term break down at any point and allow the droplets to fuse, or does it mean that the droplets are essentially always separate?
That's a good question. Well, it really depends on the strength. In principle, what we observe is the following. I mean, take this picture, right? N is, strange enough, there is no number measuring, if you wish, the intensity of the near contact forces versus the capillary forces. These are the two contenders, right? Capillary forces want coalesce, and the near contact want to prevent coalescence. So when this number goes to 0, of course, you have coalescence. And what we found is that if you wanted, for instance, a soft flowing crystal, namely droplets which do not coalesce and flow orderly, so the soft flowing crystal, the near contact forces have to be somehow 1/10 of the capillary forces. And as soon as this number goes above 1 or close to 1, namely when the near contact interactions are exceeding capillarity, then not only the droplets do not coalesce, but they are disordered, so they kind of bounce around. So I would say that I cannot give you exactly the number, but for certainly the droplets are allowed to coalesce, presumably when you are, below 0.1, when a capillarity is more than 10 times larger than the near contact, then you would start to melt, if you wish, the crystal. But I don't have the exact number. I mean, this is you can find the detail in this paper, and I don't think we inspected exactly at what value you have the let's call it melting. But certainly, I mean, it's a matter of the ratio of this near contact versus capillarity, and both can be tuned independently.
Okay, thank you. We have another question in the chat box as well. So this is from Daryl Overby. You had mentioned surfactants, and I was just wondering whether you get Marangoni effects at the interface and whether the Lattice Boltzmann method is able to account for this.
That's, again, a very good question. Yes, we do get Marangoni. Unfortunately, I don't have I don't have the slide on me. But we didn't really inspect them very, very carefully. We have a paper, I think 2 years ago. The first author is, well, you can email me and I will send you the paper, where we looked into actually the recirculation pattern near the interfaces. And there were patterns which were kind of reminding Marangoni, but we are not sure they are exactly Marangoni. But it's again, that would be an interesting direction to explore, because the way these interfaces actually interact is very, very complicated, because that depends on the fluid, but the fluid is affected by the interface. So it's a very complex chicken egg problem. And you have also to make sure that you resolve this physics. So you have to be very, very careful. But I think, yes, there are Marangoni effects, Marangoni-like effects. We have seen something similar, yeah.
Yeah, I had another question, actually, myself. The sea sponges that you showed it near the end, I think I was surprised by the flow profile, because I was imagining they were they're quite profound in the sea level. So do you have actually what's the kind of flow you have at such a depth?
Yeah, that's a very good point, Brenna. We investigated several scenarios because we compared actually the actual Euplectella geometry with the cylinders, with and without holes, just to see the effect of the texture. And some of these comparisons were done with periodic boundary condition up and down, whereas, of course, if the Euplectella is sitting on the bottom of the ocean, there must be, of course, you cannot use periodicity. So for the full Euplectella geometry, there is actually a solid wall underneath. But the Reynolds numbers, I mean, so there is somehow a layer near the wall, but the Reynolds number are not very high. We are talking, I don't remember now, less than 1,000. So as far as we can tell, but again, it's something that should be investigated perhaps more thoroughly, they don't seem to have any major effect on this, recirculating pattern inside, because there is actually, you can say that this is turbulence, some pre-turbulence, let me call it this way. And but it looks like this phenomenon basically is not, I would say, tightly coupled with the structure of the layer near the wall. But it's something that indeed should be investigated in more detail.
I would like to also ask a question about the sea sponge.
Yes.
It's really cool. So this feeding, I'm just wondering, you can think of many organisms like algae, which forms porous structures underwater, and they probably have some similar kind of flow behaviors, but at the same time, this round conical shape or cylindrical shape probably is the key to this. Some of the function, at least, like feeding, it has to be round shape, so that the flow kind of goes around inside of the cone, I guess. But I'm just wondering, like, how much of it is due to sort of that reproduction bits? Maybe I didn't catch it, but is helical spiral, is that the one outside?
Well, maybe the picture is not. Again, I'm really, as I said, I'm really not an expert in this kind of biological marine biology. But my understanding is the following. You see, these vortices are such that if you have a little organism which is captured outside, it's kept inside for much longer than it would if it would just flow away. Okay. Now, and you are absolutely correct, it's not just recirculation, it's really helicity, it's the spiral motion, which actually allows these somehow organisms to stay much longer within the structure and actually reach out to different regions. Now, this, if you wish, is the function of hydrodynamics is to somehow promote and enhance residency time within the structure and also contact between different points of the structure. And that's where I have to stop because I really don't know the details, but it apparently, I mean, the first thing we thought is, oh, okay, you can feed the structure itself. Actually, you can even feed host because there are, I don't know the word in English. I think you can, this animal, how do you call that in English? Mollusk.
Crabs?
This is an animal, you can see that. Yes. It's just sitting in between two flowers.
Crab.
It's a sort of crab, yeah, it's a sort of crab. So my reaction was, oh, the Euplectella is very nice, it's very polite, it feeds his guest animals, but actually I didn't realize that the Euplectella is a living animal itself, and the people who know much better than me told me, no, I mean, that's mostly to feed itself. As to sexual reproduction, again, I know even less, but apparently there are these gamete, I don't know how you say that in English, gamete, I don't know how to pronounce that, but you see what I mean. And so these recirculation favor encounters, and these encounters give rise actually to reproduction function of the Euplectella itself. I mean, in the paper there are details, but they were really, and the people, our co-author did really very serious work searching the literature for this mechanism. I'm not knowledgeable on that, but I can send you, actually the paper you can download it, it's on the archive.
Yeah.
And even though I wonder, maybe the archive is the first version, because we added all these details in the second revision. So I'm not sure, maybe the archive is still as the, anyway, just let me know and we can send you the updated version. But I don't know the detailed mechanism. The fact is that everybody was expecting drug reduction, right? Because it's a porous medium. Even though I have to tell you, frankly speaking, quite plainly that when we talk to the expert, we are not, this is just a foray in a different domain. We are not expert of this structure. We talked to the expert in Harvard, and they told us, and they are expert of the structural properties. They said, well, fluid dynamics is likely to be irrelevant. Actually, we asked them to join the project, and they said, no, it's not interesting. Sorry, it is interesting. But the drug reduction part was expected. This feeding and reproduction is just because we saw these recirculation patterns. Because if the flow would have just gone through the Euplectella more or less straight, maybe a little bit slower, but without this spiral structure, then it would have been much less interesting. And this you only know once you run the simulation. And again, I have to stress, this is not an ordinary simulation. Here we resolve the real geometry, which is 10 micron, all the way to the centimeter. So you need a huge computer to do that. And if you run a smaller simulation, maybe you still see them. I don't know. But I mean, in our case, we really wanted to have the real geometry up to the scale of the object. And people who run fluid simulation around this object, they use ANSYS, finite elements, and they can by no means get any close to this resolution. So probably they missed these details. I would say it's a typical case where really large-scale computing makes the difference. And we made a strong point about that in the paper. We call it, I think the title is Extreme Simulations, blah, 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 Reveal. So we use the word extreme simulation. So it looks like it's something that the experts have missed just because they didn't have enough power, fluid dynamic power to reveal, in fact, what's going on inside the structure. But again, this said, we are not expert, but as I said before, I'm really encouraging Giacomo, which is still young enough to go after, to keep going into this direction, because I think there is a lot of work to do. Absolutely.
Yes, Daryl asked a follow-up question on that. He said, maybe I missed it, but do the internal helical flow patterns follow the external helical fins?
Yes and no, in the sense that the characteristics of that's a very good question. If you remove the helical, the structural motifs, the pattern would change a lot. That is for sure. Otherwise, of course, again, it would not be interesting. So it looks like, yes, if you actually, we ran several, now I show you just one geometry, but justly the referee asked us, oh, what if you perturb the geometry, right? Because, you know, just for statistical confidence. So we did perturb the geometry, but not very heavily, because it looks like, I mean, you can have scars in this geometry, or you can have holes. So you have accumulation of mass, or regions where mass has disappeared because, you know, maybe some animal has been biting. But it turns out that if you generate changes of mass above, say, 10%, the organism would die. So we did this study. We studied, I think, 50 different configurations, but with small perturbation on top of the actual geometry. And that's a good point. I mean, if we compare this with cylinders with holes, but if you change the geometry significantly, I think the pattern would be completely different. So that there is, for sure, a sort of functional purpose into the structural property of this. Into the motif. And not all, but it's not only for the structural property, you know, how they deform, or they resist to mechanical loads, but there are these new functions that were totally unanticipated. You cannot see them unless you run a very high resolution fluid dynamics simulation. It's an open world. I mean, there is, I'm sure there is a lot of work to do. But again, I hope each of my young collaborators will pick up a direction, and I cannot do everything myself. I'm just happy to sit in the background. I'm only happy to see that there are directions to go for the future. But this is a different code, by the way. Sorry, I want to mix things up. This is a plain lattice Boltzmann, no near contact interaction, no multi-component. This is plain lattice Boltzmann, except that it is super optimized for parallel computers. I mean, it's a 5 petaflops simulation, and you know, it's 50 billion grid points. It's not a world record, but it's getting close. So you really need huge computers. We use the Marconi computer, and for some magic, we were able to get 1/10 of the machine, which is really not simple. It takes a lot of public relation to get. Marconi is 100, I think, is in the top 10. It's here in Italy, happily enough. So if ever we manage to make it nature, we will certainly make a lot of hand waving also on the press, somehow, scientific press, because we will celebrate, if you wish, the Italian technology, let me put it this way, which doesn't happen very often in this country. You are much more used to that in UK, right?
Well, I'm really looking forward to reading this paper, and this might be a good point to stop the formal Q&A session and stop the recording, and officially thank Sauro for a fantastic talk. But
thank you. It's my pleasure. It's always so refreshing to talk to people